on calculus. So basically, if you take one function that is y is equals to 1 upon x, okay, this is one function. So if I want to plot this function in graph, see, accordingly here, so if I plot this graph, so this graph is look like this, okay, the graph is look like this, y is equals to 1 upon x, okay, y equals to 1 upon x, yes. If you put 1 here, then it will be 1, 1 by 2, 1 by 3, 1 by 4. This graph is actually decreasing in order, okay, actually decreasing in order. It is 1, 1 upon 2, 1 upon 3, 1 upon 4, plus 1 upon 5, in this way, okay, in this way. So see, now after it will become 1 upon n, actually it become 1 upon n, so then the function becomes 0, isn't it? If I put this, then the graph will be like this. If I take extending on, then the graph will be like this, isn't it? The graph will be like this. Actually it is parallel, okay, in this way it is parallel. The graph will be like this, isn't it? So now see, if I take the graph like this up to this, and then after this, if I move this curve, okay, this curve along x-axis, then the figure will be like this. Okay, here I'm showing that figure. It's like will be like this. If we rotate this along x-axis, the figure will be like this. Figure will be like this, isn't it? Figure will be like this. So this is looks like a horn. That's why this figure is known as Gabriel horn. In this figure, the interesting fact is that the volume of this volume of this figure, it is Gabriel horn, is converges, but the surface area of this figure is diverges. So that's the interesting point, okay, that's the interesting point. So actually in this lecture I will discuss, or I will do mathematical analysis on this Gabriel horn. So please stay with me, and after few minutes you will see that how this the volume of this card become, you may say it diverges, sorry, the volume will be converges, and how the surface area is diverges. So let us do, okay, let us do. So see, actually I would like to make this figure, okay, this figure like this, okay, it will become like. So here, if you zoom it, this picture or this figure, then it will be like this, isn't it? It will be like this. In this way it becomes, and it goes on and goes on, isn't it? This small cylinder, cylindrical, isn't it? It's a way to describe this figure. It's like a cylinder, small cylinder, isn't it? Small cylinder. You may say it is also known as Dick's method. To prove this the volume, we would like to discuss, we will go through, you may say, Dick's method, okay, we will go through Dick's method for finding the volume, or to obtain the volume. Okay, see, now the radius of this function will be like y is equals to 1 upon x, that is the radius will be equals to 1 upon x. Here it will be 1 upon x, the radius will become 1 upon x. And if it is a side view, okay, it is side view. If you make this view, it is like this, okay, it is like this. This is side view. This side view. of this function, this side view. If I want to zoom and if I want to make in this plane, okay, in this plane, then it is a front view, okay, it is a front view. So in front view it will become radius will become 1 upon x, okay, it will become 1 upon x, and here okay, it will be 1 upon x, and this distance is there, isn't it? This is a very small distance, is dx. This is the height of a cylinder, okay, this is the height of a cylinder. And now see, the height is considering that height is dx, that is dx, isn't it? That would be dx. So we know the volume of cylinder equals to pi r square x, or pi r square x, isn't it? Pi r square x, yes, pi r square x, we know. So now see, yes, so it will be v equals to pi r square, here x is dx, isn't it? And r, it is r will become 1 upon x whole square, and x will become dx. This is the height of this function will be dx, isn't it? It will be dx. Height of this you may say it as figure, not function, it is the figure, is dx. It is very small height. This is a side view. This is the side view of this picture. You must consider this only, okay. This is actually it is small cylinder. It's small cylinder, small cylinder. So I would like to find one cylinder, one small cylinder, and after that I would like to integrate through the figure, okay, to finding the volume. So see, yes, yes. So if you integrate here, you get the volume. dV is equals to pi, sorry, it will be dV equals to pi 1 upon x square dx. So see, if you find the volume, if you want to find the volumes, and then it will becomes the limit. See, the limit will be become from this is 1, isn't it? If the function, if you put 0 here, then it will become infinite. Yeah, it will become infinite. So we have to calculate this from function 1. It is from function 1, and it goes up to infinite, isn't it? It goes up to infinite. So it will approaches up to infinite. So it becomes infinite. So it will become v is equals to, if I take the limit, it is improper integration. We all know the improper integration, I think so. It will become t goes to infinite. And the limit will be from 1 to t, pi 1 upon x whole square dx. So from here see, v is equals to limit t tends to infinite, integration from 1 to t. And if I put the pi before the integration, because it is we can remove, not remove, we can take the pi before the integration, because it is a constant term, then it will become 1 upon x square dx. V is equals to limit t tends to infinite, okay, t tends to infinite, it will be pi, yes. If you do the integration here, it will be x to the power minus 2 plus 1, then it will be 120. Okay, so v will be equals to infinite p, and here see, here minus 2 plus 1, so it will become 1 minus will be here, 1 minus will be there before the function, 1 minus will be there, it will be equals to x 1 upon x, then it will be 1 upon x. If you put the limits here, v equals to minus limit t tends to infinite, or pi, or you may take the pi before the limit also, and 1 minus sign is also there, okay, 1 minus, this minus sign will be there, continues, this minus sign continues here, so it will be 1 upon t minus 1. So v will be equals to pi. If we put t limit, if you put the limit here, that will become minus 0 plus 1. If you put infinite here, then 1 upon infinite will become 0, then the volume will become pi. So this shows that the volume of this Gabriel horn, or this figure, this figure, okay, this figure, okay, yes, like this figure, okay, this figure is pi. But when we actually calculate the area, surface area of this function, of this curve, then we'll see how things differ, okay, how things differ. So we got the volume, volume is equals to pi units, cubic units, okay, cubic units, cubic units, not units, cubic units. So now I would like to calculate the surface area of this function, of this curve. If you consider this curve, I already told you that if you take this curve, it is a diagram of this curve, okay, of this figure also, of this curve. See, now if we cut this and cut this in such a way, okay, in such a way, if we cut this curve in such a way, that is, we first of all cut this one, and here will be, here I am saying that it become one first term, okay, it looks like a first term, isn't it? It looks like a function. This curve looks like a first term. If you go on and on, if you go on and on, it will become first term, isn't it? It will become first term. So now see, if you want, if I calculate this first term, this surface area of this first term, and after that, if I put the limit, or if I find the throughout the surface, throughout the surface, that is 1 to infinite, then also it is possible. If I first of all, if I find this portion, or you may say find this area of the surface area of this first term, then we will easily calculate the surface area of whole diagram, or whole Gabriel horn. If I put the limit from 1 to infinite, then it is possible, isn't it? It is possible. So see, how will you calculate the surface area here? I am taking this first term, okay, I am taking this first term first. I am using this first term here. So it will be dx, it will be dy, and it will be dl. Yes, it will be dl. No problem, it will be dl. And we know that surface area of this first term is surface area of this first term. So surface area of S. I'm just using the surface area of first term. Okay, F is first term. 2 pi r l. Isn't it? 2 pi r l. Okay, surface area of the function. First term. Sorry, first term. So to find the dl here, isn't it? To find the dl here, this is dl. So how will you find this? Basically, it is very easy to find dl. Dl will be equals to root under dy whole square plus dx whole square. So with dl will be equals to, yes, it is length. Will be, if I put here dy, isn't it? A function, so it will be dy. Yes, yes. If you take a small algebraic calculation here, it will be dy upon dx whole square plus 1. Little algebraic calculation I did here. So here function is y equals to 1 upon x, and if I differentiate this function, it will be dy is equals to x to the power minus 1, minus 1 x to the power minus 2 dx, and dy will be equals to minus 1 upon x square dx. Yes. So first term will be 2 pi r is what here? R is dx. Dx is the r. So dx, sorry, r is 1 upon x, isn't it? R is 1 upon x, and L, here L will become dl, isn't it? L will become dl. So see, it will be SF will be equals to 2 pi 1 upon x. Here r is 1 upon x, and dl become root under dy upon dx. Dy upon dx will become this dy, and if you take here dy upon dx will become 1 upon x square, 1 upon x square whole to the power square plus 1, and dl become, yes, okay, I am using just this term, okay, dl, nothing else. I am just put this term here, okay, nothing else. Very easy to calculate. 2 pi, it will be 1 upon x integration 1 upon x to the power 4 plus 1 dx. Now if you integrate this one, if you integrate the limit, that is 1 to infinite, then what we will see now? That's the question, isn't it? That's the question. Now see here, SF will be equals to, I'm taking here to here, okay, 2 pi integral from 1 to infinite 1 upon x root under x to the power 4, it will be 1 upon x to the power 4, yes, 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 dx become, now see, 2 pi integral 1 to infinite 1 upon x root under it will become x to the power 4 plus 1, and there will be root and power cancel, it will be x square, I think 2x square, isn't it? Yes, dx, and whole term will multiply here, so it will be x cube. Or you may take yes, no problem, if you take here, no problem at all, it will become x square. Now see, this term is always less than this term, isn't it? This term is always less than this term, see, always less than this term. Sorry, it will be always greater than this term. It will be x to the power 4 plus 1 upon x square. This will be x square, x cube, and it will be x square dx. Up to this, is it clear? So I just use the inequality concepts here, okay, I'm just using the inequality concepts here. So see, this term is always greater than this term, okay, this term is always greater than this term, greater than equals to this term. So we may, if finally calculate this one, then we will easily find this one, because it is always greater than equals to, okay? It is always greater than equals to this one. So now if I calculate here, that is SF is equals to 2 pi integral, if I take the limit, because it is improper integration, I would have to take limit here, it tends to infinite 1 to t x, so it will be 1 upon x dx. So SF, the surface area of first term will be 2 pi, it will be log x, isn't it? Log x, natural logarithm, and we have to put the limit also, limit t tends to infinite, and here also SF will be equals to 2 pi. See here, it will be limit t tends to infinite log t minus log 1. So always natural logarithm, put natural logarithm here. So SF will be equals to 2 pi. If you put infinite here at t, then it will become log infinite, and the value of log infinite will be infinite only, and log 1 becomes 0. So into infinite will become infinite. So actually by this way we can say that surface area of this Gabriel horn is is in the divergence approach, isn't it? It is in divergent approaches. So after this by using this Gabriel horn, there is one known as painting paradox. Okay, you may say that it is, what is painting paradox? There is one paradox which we will discuss now. It is painting paradox. Okay, up to this, is it clear? I think it is clear now. If there is if there is any problem, please write on comment section. I would like to rectify all the problems. Okay, I would like to rectify all the problems, and if there is any queries also for this Gabriel horn, you may ask on the comment section. Okay, the comment section. So now see what is painting paradox. This is the actual picture, isn't it? This is a picture of a Gabriel horn. It is the radius here. What do you may say it is? If why it is known as painter paradox? Okay. See, if you put pi amount of paint here, pi amount of paint, if we put the pi amount of paint here, then it will cover the whole distance, or you may say it will cover the whole distance, because see the volume is pi cubic units, so it will cover the whole distance that up to downward direction. But the problem is that you can't paint the whole surface area of this figure. That is, this, if you put this paint here, pi amount of paint here, then it will cover whole the distance. But you can't cover, or you can't coat the whole, that is whole figure by paints. It is because surface area is infinite. So how will you cover, or how will you coat the figure with paints? So that's why this concept is known as painter paradox.